Okay, we're going to learn how to recognize when oxidation is occurring and when reduction is occurring. This is using oxidation level, and you learned way back in 1202 that oxidation is loss of electrons and that reduction is the gain of electrons. Well, we don't have ionic compounds all the time with carbons. In fact, most of the time it's covalent. And so we're not really looking at loss or gain of electrons. We're really looking at just loss of electron density or gain of electron density. Now, your book actually is talking about breaking carbon hydrogens or carbon-carbon bonds and forming carbon oxygen, carbon nitrogen, and carbon halogen for oxidation. And my way of doing it is just to count the number of oxygens, nitrogens, halides, or the number of hydrogens. It's easier just to count. If you increase your number of oxygen, nitrogens, or halogens by 1, or if you reduce your number of hydrogens by 2, that's going to be 1 increase in oxidation level. And to get a decrease in oxidation level, what you do is decrease oxygen, nitrogen, or halogens, or you reduce your number of hydrogens by, increase your number of hydrogens by 2. So here's an example. Here I went from an alkane to an alkyl halide. When I did this, I actually removed a hydrogen and added a halogen. So this is an oxidation. If I look at this, I can see that I went and I formed 2 oxygen bonds, and I broke 1 carbon bond. I'm forming 2 oxygen bonds, so you have 2 steps up in oxidation level. Reduction is just the opposite of oxidation, and so we can look at this down here and we can say that going from here to here I gained 2 hydrogens. So that's a decrease in oxidation level. It's reduction. When I go from an alkyl halide to an alcohol, I'm just changing a heteroatom to a heteroatom. I'm not changing my oxidation level on the carbon. If I go from a carbon-oxygen double bond to a carbon-oxygen single bond, you can see I'm breaking an oxygen bond and I'm adding in some hydrogens. So this is reduction. Your book actually gives you groups for you to compare. Alkane is the lowest level of oxidation. Then we go to 1 heteroatom or 1 double bond. Then we go to 2 bonds to a heteroatom or a triple bond. Then we go to 3 bonds to a heteroatom. And then the final thing is 4 bonds to a heteroatom. And so when we go up 1 level, that's 1 step in oxidation. If we go down 1 level, is 1 step in reduction. Why is it useful to know all this about oxidation and reduction? It's really useful in selecting reagents, because if you can look at the reagent and then the product and see that oxidation is occurring or that reduction is occurring, you can pick an oxidant or a reducing agent as your correct reagent for that step. Okay, here's a you try it for you. Did oxidation, reduction, or neither occur in each of these steps? Okay, in the first step, I see I have 2 thiols, and they get joined together into what's called a disulfide. If I look to go from here to here, I had to remove 2 hydrogens. So this is oxidation. To take ethanol to acetaldehyde, in the second step, you see I have to remove 2 hydrogens to go to this to the acetaldehyde. So that is oxidation. When I go and I take this carboxylic acid and this alcohol and I join them together and remove water, I get this ester. What happened? Well, I removed 2 hydrogens and I removed 1 oxygen. Removing the oxygen is reduction. Removing the 2 hydrogens is oxidation. So the net change is actually nothing. You actually didn't change any number of bonds to oxygen for a carbon to an oxygen, because this carbon has 3 bonds to oxygen, this carbon has 1 bond to oxygen. And if I go back and look, this carbon's going to still have 3 bonds to oxygen, and this carbon's going to still have 1 bond to oxygen. All we did was remove water. So this is called a condensation, or in some times when we remove water, it's actually called a dehydration. The removal of water is never going to be oxidation or reduction. In this 4th reaction, we're taking a C6H10 compound, and it's being changed to a C6H14 compound. This one's really easy to recognize. We go from 10 hydrogens to 14 without a change in the number of carbons, so that must be reduction. If I look at the bottom reaction, I can see I'm going and I'm adding hydrochloric acid to a compound. The addition of hydrochloric acid to a compound, you're actually breaking a carbon-carbon bond and you're adding the hydrochloric acid across a double bond. You would find that your oxidation level is not changed at all. You add a hydrogen, that's reduction. You add a heteroatom, that's oxidation. Net change is 0. What's oxidized and what's reduced here? If I look at this reaction, you can see that this is ethanol and it's taken to acetaldehyde. To go from ethanol to acetaldehyde, I had to remove hydrogens. That's oxidation. And if I look at this nitrogen-containing compound, you can see a hydrogen was added, so that's reduction. And you remember way back in 1201, 1202, we called every reaction redox. So for every oxidation from here to here, we have to have a reduction from here to here. And this is actually a biological reaction. This is NAD is changed to NADH, and in the process, ethanol is changed to acetaldehyde. So it's a redox reaction of ethanol being oxidized to acetaldehyde and NAD being reduced to NADH.